can look at those homework problems. Here they are. Okay, very good. So I'll start taking a look at those. Let's see. It looks like you are continuing to number all the pictures, so that's good. The problems didn't specifically say to number, but they don't need to. We talked about how for a beginner, you should just be your default should be to number every carbon in every picture. So it's good that you continue to do that. Let's see. 2, 3, 4, 5. Nitrogen 6. Good. Now, if you look at that first problem, if you remember, this was one of the types of problems that you had missed in the first set of homework problems. If you remember in the first set of homework problems, when you saw problems like this, you were breaking both of the bonds between the oxygen and carbon 6, and you had the oxygen off on its own as a separate atom. So we looked at that one for some more practice, and this time you got that right. So we saw here that when there's a tail of an arrow on a pi bond, it only breaks the pi bond. It doesn't break both the pi bond and the sigma bond. Okay, good. Okay. All right, so let's take a look at the next problem. So 1, 2, 3, 4, nitrogen, 6, H5. Good. And again, the second problem was one that you had missed in the first set of problems. In the first set of problems, when you saw a situation like this, you were breaking both bonds between the oxygen and carbon 6. But now we're getting that correct. We're only breaking one of the bonds between the oxygen and 6. So that's right. And how many charges should we change on every step of every mechanism?
2.
2. And you're doing that, so that's good. These first two problems illustrate one of the most common pitfalls that people fall into that we've talked about before. When we have a neutral atom at the beginning of the string of arrows, people often forget to change its charge to positive. But you're doing that correctly. When there's a neutral atom at the beginning of the chain of arrows, oftentimes people forget that the charge has to be changed to positive. But you got that correct in both of those problems. Let's look at the third one. Let's see. So in that third problem, why did you put the positive charge on carbon 3 rather than putting the positive charge on carbon 2?
I had the carbon 2 attached to that hydrogen, form a new bond with that hydrogen, whereas carbon 3 broke a bond. It lost electrons with carbon 2.
Okay, good. However, why did you decide to attach the hydrogen to carbon 2 instead of attaching the hydrogen to carbon 3? Since the tail of the arrow is between 2 and 3, it seems like that arrow might be ambiguous.
Sure, yeah, and I put it so that, there would be a tertiary carbocation, which is more stable than a secondary carbocation.
Okay, excellent. Very good. So we talked last time about how when there's the tail of an arrow between two atoms, that arrow might seem ambiguous, but there's usually a way to figure out how to interpret it. Good. And do you recall why are tertiary carbocations more stable than secondary carbocations?
Is it because it spreads the charge better?
That's true, but why do they do that? Why does a tertiary carbocation diminish the charge more than a secondary?
Because you have 3 electron-donating carbon chains attached to a tertiary carbocation.
So the key thing you mentioned is that carbon chains are electron donating. Good. And maybe the other thing to mention is a carbocation electron poor or electron rich?
Poor.
That's why it wants electron donors around it. Okay, good. So I'll look at the fourth one. Let's see. Looks like you changed 2 charges there as well. Examine the portion of your diagram that's next to the nitrogen. I think there's a mistake there. What's the mistake in the portion of your diagram on the nitrogen end?
There's another hydrogen attached.
Okay, that was probably perhaps just a careless mistake where you lost the hydrogen. So that's just a little detail to watch out for. Can you draw that in there for your notes to get that correct?
Yeah. Might take a second to show up.
Huh. Okay, there it is. I hope we don't continue to have that delay throughout the session. All right, so that's good. Okay, all right. Now those little details are important, so it's important to be in the habit of double checking to catch those mistakes. This is like math, where we need to get every single little part of the problem correct. So that's a little detail that's important to double check for. Otherwise, that picture is correct. So let's look at the next problem.
Okay.
Let's see. So I guess I'm looking at the fifth problem now. Now, remember how many charges... Oops, I thought you had made a mistake there, so I was going to investigate that, but actually now I can see I was the one who was misinterpreting it. Okay, so it looks like you got that correct, actually. Good. Now, in that problem, the tail of the arrow is between carbon 3 and the hydrogen. The tail is between 3 and the hydrogen. So it might be ambiguous. Should you form the new bond between the hydrogen and 2 or between 3 and 2? So why did you decide to form the new bond between the hydrogen and 2 rather than between 3 and 2?
Because trying to remember the rule for that. Well, I can't quite remember the rule for that.
Okay, so that one you might have done somewhat automatically without thinking through all the aspects of it. So did you form a sigma bond or a pi bond between the hydrogen and carbon 2?
A sigma.
That's right. Suppose you had formed the bond between 3 and 2. If you had formed a new bond between 3 and 2, would that be a sigma bond or a pi bond?
It'd be a pi bond.
That's right.
And the arrow would point to the previously existing sigma bond.
Okay, yeah. So I think maybe now you're seeing why the way you drew it was better, was correct. The arrow that we're seeing here, this arrow is not just telling us to form a new bond with carbon 2, it's telling us to form a new sigma bond with carbon 2. How do we know that we're supposed to form a new sigma bond with carbon 2? Because the head of the arrow is directly on carbon 2. Okay, and yeah. How would we know if we were supposed to form a pi bond? Well, as you mentioned, if we were supposed to form a pi bond, then the head of the arrow would be on the bond between 3 and 2. Okay, well, so we know we're not going to form a new bond between 3 and 2 because that would have to be a pi bond, and this is not the right type of arrow for that. So you did draw the picture correctly, but it's important to know what the reason is for interpreting the arrow that way. So let's scroll down somewhat so we can look at the next batch of questions. Good. So let's see. So you formed a new bond between 3 and 8. 8 attached to 3, then 4, 5, 6. So in this example, the tail is between 4 and 8. So why did you form the new bond between 8 and 3 rather than between 4 and 3?
Because the head of the arrow is pointing directly on the carbon number 3 rather than on the sigma bond between carbons 3 and 4. So a new sigma bond needed to be formed, and that could only be done by carbon 8 attaching to carbon 3.
Okay, that's a very good explanation. That's exactly right. Okay. That's a complicated reaction, but you got that right. So let's look at the next one. Let's see. H3O plus. Okay, that next example looks good. So let's look down to the next page. All right. 6 attached to 1. 1 attached to 2, 3, 4. Good. Now we're getting somewhat more complicated carbon chains where it helps to put in all the numbers to make sure that we're numbering those correctly. Now, let's see.
Yeah.
How many charges should we change on every step of every mechanism?
Oh, there should be 2 charges changed.
Good. So who are the two atoms whose charges need to change on this mechanism?
The magnesium bromine and the oxygen at the end of the arrow chain.
Good. Now, the problem with that, though, is you mentioned, one of the things you mentioned was the magnesium bromine. Now, that's not an atom. Who's the atom whose charge is going to change?
Magnesium.
Good. So it's good to be precise there. But I don't think you drew that. So it's important to be in the habit of forcing ourselves to always draw the two charges that changed. So let's add that in.
Oh.
Okay, good. I'm not sure if you had any particular reason for leaving that out here. You might have been thinking that you could leave that out because we've said that when there's a positive charge on a metal, it's just a spectator ion. However, in this case, the magnesium started neutral. It didn't start positive, so it didn't start as a spectator. So in this case, it's important to draw it because it did participate in a way in the reaction. Going forward, if we did another step of that mechanism, we could probably start to ignore the magnesium bromide because we could treat it like a spectator ion. But in the first step, it was participating because its charge was changing. So it's always important, it's always good to force yourself to draw that we're changing two charges. Instructors might not require that on the test, but it's good for a beginner to do that to force themselves to build this habit of always changing two charges on every step of every mechanism. All right, so let's see, looking at the next example, there you changed two charges. You left out the lithium because that was just a spectator. And the way I've drawn it here, so you showed that hydrogen H2 gas was being formed, and the way I've drawn it, you would get a positive charge on the aluminum. Okay, very good. Actually, I misdrew that example. The aluminum would not have started neutral in that example. If it did start neutral, it would become positive the way you drew it. But I miswrote the problem. Maybe let's do it correctly now. I should have put a negative charge on the aluminum at the start. So let's redo this. Let's put a negative charge on the aluminum at the start. And then let's draw what the products would be. Okay, excellent. So you did that your problem originally correctly, given the way I had written it, but this is the better way to write it. And that doesn't change anything else. Now, now that we've drawn it this way, the tail of this arrow was between the aluminum and the hydrogen. So why did you form the new bond between the aluminum and the hydrogen? But why did you form the new bond between the H and the H rather than between the aluminum and the H?
Well, it looks like this was holding a negative charge, and it would prefer to lose electrons and become neutral rather than gain or maintain the same number of electrons.
Okay, so the point here is that since the aluminum has a negative charge, it wants to lose the electrons in the bond, not just shift them around. So this is the way to get rid of that negative charge. We should have mentioned something similar on the previous example. Going back up to the previous example with the magnesium, the tail of the arrow was between the magnesium and carbon 6. So why did you form the new bond between the magnesium and carbon 1 rather than, why did you form the new bond between 6 and 1 rather than between the magnesium and 1?
Well, I think we did not want to form a carbocation, the secondary carbocation, and so we could combine it or make a sigma bond with carbon 1, and 6 would then be left neutral.
Okay. Now, is it possible to form a secondary carbocation? Is that an allowed or unallowed type of carbocation?
It's allowed.
That's right. So we have to go into that in a little bit more detail. We're going to get a positive charge either way. The way you drew it, you ended up with a positive charge on the magnesium. So how do you know it's better to put the positive charge on the magnesium instead of on carbon 6?
I think the magnesium can hold that charge better than a carbon would. It has an electronegative bromine donating to the magnesium to help stabilize that ion.
Okay. Okay, now that explanation turns out to be a little bit confused. For one thing, if you're electronegative, does that mean you're donating electrons or withdrawing electrons?
I guess they would be withdrawing, yeah.
Which kind of almost contradicts what you had said earlier.
Right.
So, in any case, we went through a different way. We went through a different way of thinking about this in our last session. So, someone is going to have to lose electrons, either 6 or the magnesium. Who wants electrons more, a carbon or a magnesium?
A carbon.
How can you tell?
It is further to the right. It's more electronegative, I guess.
That's right. Or you can say because it's further to the right in the periodic table. So who's more willing to lose electrons? The magnesium or a carbon? Magnesium, because it's further to the left in the periodic table. That's the best explanation here. Someone has to lose electrons. The thing that's best to lose electrons is the thing that's furthest to the left in the periodic table. Notice we don't need to bring the bromine into it to explain this pattern. Okay. So who can generally stabilize a positive charge better? Something that's further to the right or further to the left in the periodic table?
To the left.
That's right. And who can stabilize a negative charge better?
Something to the right of the periodic table.
Okay, so that's an important type of reasoning that we'll be using a lot in OChem. Okay, so this problem, again, you might have done a little bit mechanically. You might have just remembered who the right atom to use here was rather than quite figuring it out. So we just went through the logic there again of how to figure that out. You might want to write down that logic since I think you might have forgotten it. So the point here is we're going to have to, someone has to lose electrons. It's better to have the thing that's further to the left lose electrons. And notice that it's easy to get confused. Remember that for a second you were saying the bromine could stabilize the positive charge because it's electronegative. But that actually is the reverse of the truth. If something's electronegative, it would tend to destabilize a positive charge, not stabilize it. So you can see how easy it is to get confused about those ideas. Okay, so I'll take a look at the third example. I guess one thing we should say is you might have been confusing electronegative with negative. Something negative can stabilize a positive charge, but being electronegative is a completely different thing from being negative. They're two words that sound similar but mean different things. Okay, so I'll take a look at the third example. Let's see. So here we have 6 forming a bond with 2. Six, 2, 3, 4. You saw that 4 should still be bonded to 9 in the product. That's good. 5, 6. Okay. And by the way, if you look at the arrow here in the middle between 6 and 7, why did you form the new bond between 6 and 2 rather than between 7 and 2? The tail of the arrow is between 6 and 7, so why should we form the bond between 6 and 2 rather than between 7 and 2?
We had just formed a pi bond with oxygen and carbon 7, and so 7 needed to lose electrons to maintain its octet, and so that's why it formed with carbon 6.
Okay, excellent. That's right. Now, hopefully this is the type of error that you'll get comfortable with so you don't have to think through that logic each time, so it will just seem natural, like dominoes falling over, that the new bond will be between 6 and 2. Good. So you did that correctly. That's a pretty complicated reaction, that ring-forming reaction, but you got that correct. So that's good. So let's see. Next reaction, let's see. Carbon 1, 2, 3. Okay, I think this is, we did an example like this together last time and we got this incorrect because we forgot to break the bond between carbon 1 and carbon 2. But this time you got it correct. This time you did break the bond between 1 and 2. So that came out correct, good. Now, usually we're supposed to change 2 charges. Why did you not change any charges on this example?
This was cyclic. It's the one that, I guess, any atom that gained electrons also lost electrons and vice versa. So all the charges remained neutral.
Excellent. Very good. That's right, and that's a good explanation. Normally we change 2 charges on every step of every mechanism, but the big exception is when we have a cycle of arrows. That's right. Good. You might have thought when you looked at this originally that this was going to form a ring, but when you dealt with the arrows carefully, it actually did not form a ring. It broke the molecule into 2 pieces. So that's good that you took your time and just obeyed the arrows. Okay, so let's scroll down to the next reactions. Okay, let's see. So 2 connected to the oxygen. So is this a cycle of arrows?
No, it's not.
Good. I thought this one would be tricky. So did you change 2 charges?
Yeah,
Yeah, you did.
2 oxygen.
I thought this one might trick you, because at first it looks like it's a cycle of arrows to me, but it really isn't. For example, the oxygen on the far right is losing, the oxygen with a negative charge is at the tail of an arrow, but it's not at the head of an arrow. It's losing electrons, but not gaining. So this is not a cycle of arrows. It's just a ring-forming reaction. And it looks like you did each of those steps correctly. Okay. 1, 2, 3. Okay, I think that's a tricky one if you've never seen that before. So that's good that you took your time and got that reaction correct. That's very good. Okay, so let's look at the next. Here's a reaction we never looked at before. This looks a little bit weird, but it's a ring opening reaction. I think you did that correctly. That's another cycle of arrows. Notice this is a very, very small cycle. Only 2 arrows, but it's still a cycle of arrows, so you didn't change 2 charges. Let's look at the next one. Let's see, 2 connected to 5, 8 connected to 3. Okay, that second example look kind of weird looking, but you just took your time and interpreted the arrows carefully. So that's very good that you adapted to that problem. You did that correctly. Then the third example, 6 to 1. All right, that third example, again, I think is different from any of the ones we did together in the tutoring, but you adapted to that. So this is a great example of how we can start to rely less on memorization. These 3 examples here at the top are real examples from the second semester of OChem. I'm pretty sure you've never seen those reactions before, but if you just take your time and obey the arrows, you can still draw the product. So that was a very good execution of that. Okay, so let's look at the 4th example. Let's see, 3 connected to 1, 2 connected to 6. This example, did you notice, this is a different way of drawing the arrows. Normally here, remember that normally when we're forming a sigma bond, we put the head of the arrow on the atom that's gaining the bond. But I think I mentioned to you during our last session that when you're forming a ring, there's also an alternative. When you're forming a ring, sometimes they just put the head of the arrow in space between the 2 atoms that are forming a sigma bond. We don't usually form a sigma bond by putting the head of the arrow between the atoms, but when you're forming a ring, that is sometimes done. So you adapted to that correctly. We're forming a new sigma bond between 1 and 3 and between 2 and 6. When you're forming a ring, you can indicate that by putting the head of the arrow in space between the 2 atoms. Although you could still use the previous approach and also put the heads of the arrows on the atoms, like we did in the 3rd example on that page. Okay, good. Let's see, the next example involved a triple bond, but it looks like you handled that correctly. So with that last example there on the page, I was trying to trick you into forming the bond between 1 and 7. That's what most students do when I give them that example. When I give people that example at the bottom of the page, most students form the bond between carbon 1 and 7, because 1 is closer to 7 on the page, maybe. So it's good that you took your time and you obeyed the arrows there and you formed it between 2 and 7. And you just pushed carbon 1 up and out of the way in order to do that. So that was good. That was another cycle of arrows, so you didn't have to change any charges in that example as well. So let's see. I guess all the examples on this page were cycles of arrows, so you didn't have to change any charges on any of those examples. Yeah. Okay, a bunch of those were pretty tricky, but you got those right. That's good. Now this one here is a little tricky too. Let's see. So 1 and 6, 6 and 5, 5 and 7, 7 and 2. Okay, that last example is a little different from any of the ones we did together. It's kind of a weird looking reaction, although that's a real reaction from the second semester. But you just took your time and interpreted the arrows. So that one came out very well. That's a pretty tricky example, but you just obeyed the arrows and you erased the bonds you had to and formed the new bonds, and you drew some good pictures of the products there. So that's a tricky example, but you got that one right as well. Okay, very good. So I think in all of those, I'd asked you to try to double check your work and avoid careless mistakes and try to get 100% accuracy. And you came pretty close. There was only one careless mistake. Remember, there's one example where you left off one hydrogen. So that's pretty good record for so many problems. So that's good that you took your time and were double checking yourself and avoiding careless mistakes. That was almost 100%. So that was quite good. There were a couple problems there where you might have perhaps been doing the problem a little automatically and forgot the rationale. And we mentioned those as we went through. So those would be good things to review so that in a few weeks or months when you come back to this, hopefully you'll if you forget how to do this, you can remember the rationale. In particular, who would rather have a positive charge, an atom that's to the left or the right in the periodic table?
To the left.
And who would rather have a negative charge?
An atom to the right of the periodic table.
That's right. That was something that we saw was a useful rationale on a couple of the problems, or one of the problems that we had seen. Okay, overall that was very good. So that's good that you took your time and were so accurate on those problems. And you also, I gave you a bunch of problems there that were different from any of the ones we did together, but you took your time and adapted, and you got all of those 100% correct, those new types of problems. So very good. Okay, so I think that's a skill that will definitely be useful to us. Let's go back to my screen. I'll write something down here. Okay, we'll do a few more examples on those ideas, and then we'll move on to the next topic. So let's try this example. Try drawing the product based on the arrows here.
Okay. Okay.
Okay, excellent. Good. So that's good that you put in the numbers. You changed two charges. Now, this example is designed to be kind of scary and intimidating because there's this weird ring on top of a ring structure that we haven't seen before, or haven't seen very often. But that part of the molecule didn't make much difference anyway. There were no arrows in that part of the molecule, so that part of the molecule was not changing. So you just focused on the part of the molecule that was changing, and you did that correctly. Very good. I'll write something else on my screen.
Okay.
Let's try this example.
Okay. Okay. Okay, should be done with that one.
Okay. How did you know to break the bond between... Oh, there you go.
Sorry.
You double-checked yourself a little bit more. Okay, good. So that bond is between which two atoms?
2 and 4.
Okay, yes. All right, so that's part of the double-checking process. We know.
Yeah.
How do we know we should not break that bond between 2 and 4?
There are no arrows indicating that. It's not telling us to change
so
it.
we have to make sure that we don't change the parts of the molecule that are not supposed to be changed. Okay, now obviously I think conceptually, obviously you understood this problem, but it's also important to get into this habit of double-checking ourselves to make sure we're avoiding careless mistakes. Again, it's like math. It's not good enough to know conceptually how to do long multiplication. That's useless unless we can reliably do long multiplication without careless mistakes. So our goal here is not just to know conceptually how to interpret the arrows, but how to get them right reliably and efficiently without careless mistakes. Because remember that we're going to be building on top of this. This would just be part of doing a harder OChem problem. All of these problems we've been going over so far would usually not be the whole problem. They would just be part of a harder problem. But it's crucial that we get this part 100% correct. And we've been doing pretty good at that. We've had a pretty low level of errors, but our goal is to get as close to 100% accuracy as we can. So we need to get into that habit of treating this like math and being paranoid about checking for mistakes. All right, so you went back and you double-checked that. You put that in correctly. Let's see, otherwise I think that was correct. I'll go back to my screen.
Okay.
That's again why when we're doing the problems in the tutoring, I'm going to wait until you tell me that you're done with each question. That way you'll have the time to double check on your own, and then you can tell me you're ready when you've double checked that. Okay, so let me write this down.
Thanks.
And of course the point of that is hopefully you're going to build that habit for doing problems on your own as well. I'm hoping that you'll double check the problems that you're doing in the tutoring, but the important thing is that you're building the habit of double-checking all the problems that you do, so that you do that when you're doing questions on your own as well.
Okay.
Okay, so now let's try this problem.
Okay. Less than 8.
Okay, good.
Okay. Then
All right. Okay. That's correct. Very good. I'll write down another problem. Let's try this example. Actually, let's go back. Let me draw this slightly differently.
okay.
Okay. We haven't talked about this before, but when we have an electron all by itself like this, this is what's called a radical. If you remember, normally electrons are in electrons come in pairs, but this is an unpaired electron. All right, we haven't talked about that much, but let's see if we can adapt to these errors. So let's try now drawing the product.
Hmm. Okay, I'll try that.
Okay, it's good that you slowed down and thought about that a bit. Now, it looks like you haven't changed any charges on this reaction. So why did you decide not to change any charges?
Well, there didn't appear to be any changes in the number of electrons each atom had.
How do you know?
So the arrows either indicated both a gain and a shift, or a gain and a loss of electrons, so it would retain the same number, or it was just a shift of those electrons, like on the oxygen with the radical. It lost a bond with carbon-6, but it formed a bond with the hydrogen, so it retained the same number of electrons.
Okay, good. That was actually a very well-described explanation. That's right. You're right. So some of the atoms are gaining electrons, but they're also losing electrons. And other atoms are just shifting the electrons. So the way you put that was quite right. Good. So a more simple way to put it is this is another example of a cycle of arrows. This is a cycle of arrows, so we know we're not going to change any charges. When there's a cycle of arrows, we don't change charges. But the explanation you gave was correct as well. So that's right. That the positive charge on the oxygen is not going to change in this example. So that's good that you took your time and got that right. And for that matter, the radical doesn't change. There's no arrows telling us to change the radical into something else, so it starts as a radical and it ends as a radical as well. There's a little bit of a weird example, but that's a real example that comes up sometimes when you're doing mass spectrometry, which is something you might study in the second semester. Okay, good. So it's good that you took your time and thought about that. It's important to know when you have to slow down and give something some thought. So you did that, and you came up with the right answer. All right? That was good. All right, so let me write this down. Okay, let's try this example.
Okay.
Okay, this is a kind of complicated example. You ended up with three separate things, so to speak, three separate molecules, but you worked that out correctly. Good. All right, I'll go back to my screen. Let's try this example.
Okay.
Okay, let's see. Okay. Good. All right, you took your time. You drew in the new arrows we needed. The new bonds, you erased the bonds that were being unformed. And this was a cycle of arrows, so you didn't have to change any charges. We got that one correct. Very good. Let's try this example.
Okay.
Okay, that was a little bit of a complicated example, but you took your time on that. I think that's a little bit different from any of the examples we did before, but you did that correctly. Again, the most important thing here is oftentimes when there's a neutral atom at the beginning of the chain of arrows, people forget to change its charge to positive. So it's good that you didn't forget, but you did change its charge. You just always have to remember to change two charges, and we'll always make sure, if you think to change two charges on every reaction, we won't miss any charges that we need to change. Good. All right, I'll go back to my screen. Okay, well, that's outstanding. I think we made very good progress on that. So that topic that we've been going over so far is how to draw the product based on the electron pushing arrows. And right now I feel like we've got pretty close to mastery of that. I think we're understanding conceptually, and also we're making very few careless mistakes. So that's excellent. It's important to keep practicing that over the coming weeks and months because you don't want to lose that skill. But
Yeah.
I think for right now, we definitely have that down. I think that's one of the most important skills in the course. So I think we made some good progress on that. Remember,
Good.
As you go forward, the important thing is to draw the product that the arrows tell you to draw. So the arrows are our masters here. We have to obey the arrows and draw what the arrows tell us to draw. The mistake that students make is they start drawing what they expect to see, or what they'd like to see, or what feels good, or what they remember from vaguely similar problems. But those are all poor techniques. The important thing is to draw what the arrows are telling us to draw. And I think we built that habit. Well, what should you do if you draw what the arrows tell you to draw and it looks weird or wrong? Well, maybe you made a mistake, so you should double check how you interpreted the arrows, but it also might indicate that you drew the wrong arrows. But you can't tell that you drew the wrong arrows unless you first start by drawing the picture you would get from the arrows that you've drawn and see what it looks like. Okay. All right, excellent. So I think now we're ready to move on to our next topic. So what we've been doing so far is I've been drawing the electron pushing arrows for you and asking you to draw the product based on those electron pushing arrows. And that's a very crucial skill in OChem, which is why we spent quite a bit of time on it. But now it's time to move on to an even more crucial skill. As you know, in OChem, usually you're not going to be given the electron pushing arrows. Usually you have to come up with the electron pushing arrows yourself. So that's the next topic we have to move on to. The next topic is how can you figure out on your own what the reasonable electron pushing arrows are? How can you figure out what the correct or reasonable electron pushing arrows to draw are? These videos are offered on a pay what you like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.